the derivative of a polynomial function and natural exponential function. Our objectives in this lesson are to differentiate a constant function, power function, sum and difference of two functions, and the natural exponential function. The notation for the derivative of y equals f of x can look a bunch of different ways. We have prime notation, where we put the little prime symbol after the y prime, which, because y equals f of x, can also be written as f prime of x. Notice the prime symbol comes right after the f. Leibniz notation, after Gottfried Leibniz, who helped discover calculus, uses d over dx. Notice that there are different ways to show that. You've got dy dx, you've got d dx of y, which means take the derivative with respect to x of the function y, and because y equals f of x, we can write d dx of f of x. Again, this notation meaning take the derivative with respect to x of the function f of x. Prime notation and Leibniz notation are the most commonly used ones. Operator notation you might see from time to time. We don't use it much here. Let's take a look at the rules to help us take derivatives. The constant rule. The derivative of a constant, c being our constant, will always equal 0. Why is that? Well, think of the graph of a constant function, like y equals 3. That is just a horizontal line. And because derivative means slope of the tangent line, what is the slope of a horizontal line? 0. So of course, the derivative of any constant must equal 0. Easy as that. Therefore, the derivative with respect to x of the constant 3 is 0. Look at this example. The function y that equals pi dy dx must equal 0 because pi is a constant. It's a letter, a Greek letter, but it represents a number. It is a constant. Any constant has a derivative equal to 0. The power rule. This is for polynomial functions. The derivative with respect to x of x to a number n is n times x to the n minus 1. What does that mean that we do? We take that exponent, we move it, multiply it to the front as a coefficient, and then we subtract 1 from the exponent. Let's see how that works with this example. The derivative with respect to x of x to the 5th. The 5, that is the exponent, gets moved to the front. 5 times x to the 5 minus 1. Now we don't have to write 5 minus 1. Of course, that's just 4. So this is 5x to the 4th. And that's it. That's our power rule. The constant multiple rule says that the derivative with respect to x of a constant multiplied to a function is the same as the constant pulled out multiplied to the derivative with respect to x of that function. Think about how a constant multiple rule works for limits. And since derivatives come from limits, that should make sense to us. Let's take a look at this example. The derivative with respect to x of 2 times x to the 5th. This is the same as saying 2 times the derivative with respect to x of x to the 5th. Now remember up here, we took the derivative with respect to x of x to the 5th using our power rule. So this is the same as saying 2 times that derivative, 5x to the 4th. And of course, that can be simplified. 2 times 5 is 10, so 10x to the fourth. A quicker way to think about this is take that 5, and without moving the 2, multiply the 5 times the 2, and right away come up with 10. So straight from here to here, 5 times 2 is 10, and then we subtract 1 from that exponent. Our new exponent is 4. Sum and difference rule. The derivative, with respect to x, of the sum or difference of two functions, f of x plus or minus g of x, is equivalent to the derivative with respect to x of a function f of x plus or minus the derivative with respect to x of the other function g of x. This is just saying we can take the derivative of each term separately. For example, the derivative with respect to x of 2 plus x to the fifth. Notice this one, which I purposely put right below this one, 2 times x to the fifth, looks very similar, but I'm not multiplying the 2 to the x to the fifth like I was up here. I'm adding these. So I'm taking the derivative of 2, and I'm taking the derivative of x to the fifth, and then I'm adding those together. So specifically, I'm doing the derivative with respect to x of 2 plus the derivative with respect to x of x to the fifth. Each derivative one at a time, and then adding them together. What does that derivative look like? The derivative of a constant is always 0, and the derivative of x to the fifth, using our power rule, 5x to the fourth. And finally, the natural exponential function. The derivative with respect to x of e to the x is e to the x. This is our easiest one to think about because notice nothing changes. The derivative of e to the x is e to the x. This is our easiest. E to the x stays e to the x. Why is that? Well, if we think about what the graph looks like, and we think about the slope of the graph along the way, well, at first, the slope is close to 0, so a low positive number, because it still has a positive slope. And then as we move to the right, the slopes are increasing, just like the graph is increasing. Look at that. The derivative of e to the x is e to the x. That one should always be easy to remember. Let's take a look at this example. The derivative with respect to x of 4x squared plus 4e to the x. We're using our sum and difference rule because we have the sum of two functions. For the first one, we can use our power rule. Take the 2, multiply to the 4. 2 times 4 is 8, so that first one makes 8x. 2 is our exponent, we subtract 1, and it leaves us with 1. I don't have to write x to the 1, it's the same as x. Plus 4e to the x. 4 is a constant multiple, so it gets multiplied to the derivative of what it's multiplied to. What's the derivative of e to the x? Well, that's our easiest because it stays the same, e to the x. And there we have it. Let's take a look at these examples. Find each derivative using the rules from this section. When they appear, a and b are constants. Often, when we're working with variables, variables will be end of the alphabet letters. And if we use beginning of the alphabet letters, such as A, B, C, those are going to represent constants. Number 1, the function f of t equals 4t to the 6th plus square root of 2. Find f prime of t. This is prime notation telling us to take the derivative of f of t. F prime of t equals, we use our power rule for this one, multiply the 6 to the 4, 24, t, subtract 1 from the exponent makes 5. Square root of 2 is a constant. So we don't have to really think about that one. That derivative is 0. Now, of course, I don't usually write plus 0. I would just write 24t to the 5th. Number 2, y equals the quantity x squared plus pi squared minus e squared minus 3e to the x, all over 5. Find dy dx. Using Leibniz notation, we are instructed to take the derivative of the function y with respect to x. Now, before I just jump into the derivative, I notice this looks kind of messy. This is a quotient. I would prefer to write it so it's not a quotient. So let's rewrite y before we take the derivative. So it says 1/5 times that quantity x squared plus pi squared minus e squared minus 3e to the x. Now this will be better because when I take the derivative, dy dx, 1/5 is just a constant multiple. So that 1/5 gets multiplied to the derivative of each of these terms. And because these are all added or subtracted, I can do the derivative of each one at a time. The derivative of x squared using my power rule, 2 goes in front. I subtract 1 from the exponent, so it's 2x. Plus, pi is a constant, therefore pi squared is a constant, and the derivative of a constant is 0. Minus, e is a constant. E doesn't have an exponent with a variable here, so this one is also a constant. E squared, its derivative is 0. Minus 3e to the x. E to the x is our natural exponential function. There is a variable here. So this one uses our easiest derivative with the 3 multiplied in front, 3e to the x. Now, of course, we can clean that up a bit. So dy dx looks a bit nicer as 1/5 times 2x minus 3e to the x. And if we wanted to write it the way they gave us the problem, we could just put that 5 back in the denominator like this. Either of these work just fine. Number 3, d dx, which means take the derivative with respect to x of this quantity, ax squared plus bx plus 1 over a equals, this is a sum of terms, we can take the derivative of each one separately. Also remember that we were reminded that a and b are constants. When I take the derivative here, I'm using my power rule, so I'm going to multiply the 2 out in front. 2 gets multiplied to the a, and it's 2a. X, and then I subtract 1 from the exponent, and it's a 1, plus, now this one's interesting. Of course, b is a constant multiple, so we write b. This exponent right here is a 1. So we multiply the b times 1, it's still b. And when I subtract 1, 1 minus 1 makes 0. For now, I'm going to write x to the 0, but what is that actually? That's right, it is 1. So really, when I have x to the first, its derivative is just 1. I don't have to go through the subtract 1 to get 0 and think about what is x to the 0. An exponent of 2 brings down to an exponent of 1, and an exponent of 1 brings down to no x at all. Plus the last term, this has no x's in it whatsoever. That is a constant, and the derivative of a constant is 0. And then we'll simplify 2ax plus b, which is our derivative with respect to x of this expression. Now notice I did not write dy dx or y prime in front of this because they did not give me this function called y or f of x. They straight said take the derivative with respect to x of this expression. So there is nothing to call our derivative. 4. Find dc dr if c equals 2 pi r. This means find the derivative of the function c with respect to the variable r. This is like saying find dy dx if y equals 2 pi x. What would that look like? 2 pi is our constant multiple. So dy dx would equal the constant multiple times the derivative of x, which of course is just 1. So dy dx would equal 2 pi. Now, if it helps to change the letters into more familiar letters, feel free to do that. Or we can just think of it like this. The derivative of c with respect to r is dc dr. R, being our variable, has the constant multiple of 2 pi in front of it, and r is to the first. So when we take the derivative of r to the first, it becomes just 1. And 2 pi is our derivative, dc dr. Sorry guys, just noticed that this should not be a lowercase r. When we use lowercase letters and uppercase letters, they do mean different things. So let's fix our notes. This should be 2 pi capital R. Still works the same thing, the same way. This is r to the first, therefore the derivative is 1. But just to note that anytime we're working with variables, the case does matter. If this is uppercase R, this absolutely must be uppercase R. Thanks for watching.